our speaker for today. We are very happy and honored to have Gil Kalai with us. Gil made many contributions in combinatorics, convexity. He won numerous awards and honors that I will not mention here today. I'm thankful to Gil that he was kind and flexible to accommodate my request to speak about covering problems today. And Gil, please.
Okay, so it's great to be here in Tel Aviv in this sort of international seminar, and I'm very happy to come back to covering problem and to my side of the story, which is more coming from discrete geometry, but it's always very nice to see how things interlace. And I thought before I will talk about Borsuk problem as some sort of prologue, I look at the problem that Danny showed me, and it reminds me of some the area of research which a little bit, in a sense, you can say closer, and this is the area of non-convexity. So I don't know if you are all completely familiar with this, but let me tell you a little bit about it, because it is about starting with non-convex sets in the plane and study them in the tools and mindset of convexity. And in particular, a very central problem is how many convex sets you need to cover them. And there is a nice paper by Noah Nitzan from 2009 called Non-Convexity. This is a whole, and if this is something you're all familiar with, then just interrupt me and I'll move to other things. So here is a Valentine's theorem, and it says the following: if S is a compact set in R2, and for every 3 points x, y, and z, at least one of the line segments x, y, x, z, and y, z is included in S, then S is the union of 3 convex sets. So you see that the condition is a relaxation of the condition of being convex. Being convex means that for every 2 points x and y, the line segments x, y belong to S. And here we want that if we have 3 points, at least one such a line segment is in S. If we have the union of 2 convex sets, then certainly it satisfies this condition, because if we have 3 points in the union of 2 convex sets, then 2 of them belong to one of the convex sets, and therefore the line segment between these two is in the set. But it turns out that it's not true that if you have this condition, then S is always the union of 3 convex sets. And why not 2? So here is the example. This is the solid pentagram. So we have also all this area inside here, and this set, this compact set, is not the union of 2 convex sets. Not only it's not the union of 2 convex sets, if we look at the invisibility graph, the visibility graph of a set, we say that 2 points in the set are adjacent if the line segment between them, is in the set. So here, if you look at these 5 points, you see that, what do you see? You see that this and this, oops, sorry, I don't know why. That even if you look at the chromatic number of the invisibility set, you need at least 3. Because here, you have here a 5-gon that you cannot color with the same color any 2 consecutive vertices, so you need at least 3 colors. So in this case, and we can define these 3 very interesting parameters. Alpha of S is the maximal independent set in the visibility graph. So the maximal number of points that no 2 sees each other. beta, okay, maybe I miss here, but beta is the chromatic number of the visibility graph, and gamma is the mean number of convex sets needed to cover S. And you can also ask about the minimal number of disjoint convex sets required to cover S. And the study following this work from the 50s of Valentine, there is a very interesting branch of, I would say, combinatorial geometry or combinatorial convexity studying this problem. And I'll mention you some highlights of this study. One highlight, which I will not explain the precise motivation, but is a generalization of the Magen David. So on the left, you see here the Star of David. I don't know if this is the name in English. So this is the union of two triangles. It looks like this. And you can replace it by this object here, which is a triangle, and this guy, which is a generalized triangle. And this type of generalized Stars of David come to play in this series. Sometimes you even delete some points. I should say one branch of this non-convexity series, if you take a convex set and delete, say, k points, how many convex sets are needed to cover them. And there was a question, I think Brin and McKay proved that if the maximum independent set is n, then there is a finite number depending on n of convex sets required to cover S for a compact convex set in the plane. And it was a conjecture for many years that a polynomial number suffices. And this was proved by Micha Perles and Saharon Shelach. And their proof give constant times n to the 5. And this was reduced to lower degree polynomial by Ilka Matuszek and Pavel Welter. And it's a very, very interesting question. What is the precise bound? And some algorithmic aspect of these proofs. And there was another very nice question: what happened if S is not compact? And the paper I mentioned by Noah Nitzav in 2009 present the proof that if you have a set, any set in the plane, so that from every 3 points, 2 points see each other, or the line segments of 2 points belong to the set, then the set S is the union of 6 convex sets, and the number 6 is best possible. If you raise this alpha by 1 or 2, then no finite number suffices, and this result about 6, both the result and the example which shows it's optimal. I think the major part of the work was done by Micha Perles, and then it was finalized by Noah Nitzav and written, and this is a very nice paper from 2000. So the problem that Danny described to me reminded me this development. So I wanted to mention. And now I want to move to the main topic of today, which is the Borsuk problem. And this is again a problem about covering sets with covering sets. And the Borsuk problem says that the Borsuk conjecture, every set of diameter 1 in RD can be covered by D+1 sets of smaller diameter. And this was called the Borsuk conjecture. I think Borsuk posed it as a problem. Is it correct? And it was posed in 1933, and then was settled in 1993, so about 30 years ago, in the negative, and there were various partial result inverse direction. I'll talk about it. Why is the number d plus 1? So you need d plus 1 because in RD you can find d plus 1 points, the vertices of the regular simplex, and the distance between every two of them is the same. So if you want to cover them by sets of smaller diameter, you need at least d plus 1. So this is a very simple example. A more sophisticated example comes from what's called the Borsuk theorem. And this theorem asserts that if you look at the sphere, the unit sphere, or let's say the unit sphere in RD times 1/2, so the sphere of radius 1/2 of diameter 1, then if you cover it by d sets, then one of these sets, if you cover it by d closed sets, then one of these sets contain antipodal, a pair of antipodal points. So this means that if you cover it by d sets, then the diameter of one of these sets is at least 1. And this example is very different in nature than the d plus 1 point. And it's a very nice example. And first of all, it's a deep theorem in topology that this is the case. And it's not difficult to show that if you have the ball, you can divide it to d plus 1 sets of smaller diameter. The best way to see it, one way is to look at the regular simplex, the vertices of the regular simplex inside the ball, and to divide it according to the, say, Voronoi diagram, or the closest. For every vertex of the simplex, you take all the points which are closest to this vertex. So it is known that the convex ball, if you take a unit ball, then you can divide the unit ball to d plus 1 sets of smaller diameter. And the unit ball, by the isoperimetric result, it's the set of maximum volume from all the sets of diameter, of fixed diameter. So this leads to the conjecture that this will be the worst possible in terms of covering by set of smaller diameter. I should say, let me mention another problem for people who are interested in high-dimensional geometry, which is also an annoying problem. It's not known, if you want to cover the unit ball, say, with sets of smaller diameter, it's not known what is the smallest diameter that works. Okay, so there is this example that you take the Voronoi cell for the d plus 1 points of the regular simplex, but it turns out this is not the best example. And the Larman constructed probabilistically a better example, but it's not known what is the truth. So even for this very simple problem, to start with the unit ball, you want to cover it by sets of smaller diameter. What is the minimum diameter? You want to cover it by d plus 1 set of smaller diameter. What is the minimum possible diameter? There are some bounds, of course, based on volume consideration, but the answer is not no.
But Gil, the example the point you made that you cannot cover the unit ball with less than d plus 1, it's only
Yes.
when you restrict yourself to closed sets. So what happens?
No. If you talk about diameter, then you don't have to restrict yourself to closed set, because the diameter of the set is defined as the supremum of the distances of pairs of points in the set. So if it's not closed, if the closure has diameter 1, then the original set has diameter.
Okay.
Gil, this question that you ask is not known even in very low dimensions?
Okay, I don't want to commit myself to anything about dimension 1.
Okay.
And I would guess, I will talk a little bit about a low dimension as far as Borsuk problem, but the question about the unit ball, I think in dimension 2 it should be easy. And I'm not sure about very low dimension. So 3, I would guess that it might be known for dimension 3. One has to look at the paper of Larman. I wouldn't be surprised if it's not known even for dimension 4 or something. This is a good point. I'm glad you raised it. And I should say that about 10 years ago, I wrote a paper about problems around Borsuk original problem, and it has many problems. Some of them were settled in the meantime. So let me move on. Okay, so now I should say that we know that Borsuk problem is not true, but in any case, it's useful to make the following definition. F of D is the smallest number, such that every set of diameter 1 in RD can be covered by F of D set of smaller diameter. And the G of D is the smallest number, such that every finite set of diameter 1 in RD can be covered by G of D sets of smaller diameter. So we define two very similar functions, one for general set and one for finite sets. Of course, if you believe, as long as you believe Borsuk conjecture, it's a bit late for that, but if F of D is D plus 1, then this would be, then also G of D is D plus 1, and they are the same. But now it's another problem, it's another annoying question. Is it the case that F of D is equal to G of D? So probably it's not correct. So probably I don't see any reason that in high dimension these two functions are the same, except that from time to time when I ask this question, people come with proofs, convincing proofs that you can make a reduction to the finite case, except that when you check these proofs carefully, they are no longer convincing. So I'm not aware of any reduction from the general case to the finite case. I am aware to a lot of incorrect reduction that fooled me for a while, that several people propose, and I don't know what is the situation. So this is another curious question, which is interesting. Okay, so what is known about the Borsuk problem? So I want to, let me say a little bit about the low dimension cases. So it is correct, of course it's correct for D equal 1. It is correct for D equal 2. In the plane it is correct. Let me add a page. Add a page. So it is correct, for D equal 2 it is correct, and it is related to nice questions that I will mention later. The reason it's correct that if you start or if S has diameter, if the diameter of S is 1, then it was proved, as a matter of fact, about 20 years before Borsuk made the question, that you can put S inside a hexagon, okay, a hexagon where the distance between parallel edges is 1. So this was a theorem that was proved already in, I think, 1905. And from this theorem, it follows that, and then you can take this hexagon and divide it to 3 parts. Now, this hexagon has diameter bigger than 1, but you can divide it to 3 parts, which are these 3 pentagons, and these 3 pentagons have diameter smaller than 1. So this was the idea, to find a sort of a universal set that contain all the sets of diameter 1 and can be divided to sets of smaller diameter. And this works for D equal 2. And several people in the 60s managed to push this idea to dimension 3. So there were several approaches, and they didn't find a unique polytope that works for all the sets, but they found a 1-parameter set of polytope that work for all the sets of diameter 1. And this was much more difficult than the original proof. There was another approach which was based on the finite configuration of points. So, and this approach was to try to approach d equal 2 and 3, try to understand the graph of pair of distance one pairs in S. And especially for S finite. And it turns out that this question, you have a collection of points, the maximum distance is 1. What can be said about the graph, where the vertices are the point, and the edges are those pairs of points of distance, of maximal distance. And this is related to various other very nice questions that I will mention, and also to the Fracker conjecture that Shachar just mentioned, and I'll come back to them in a minute. So this is the case d equal 2 and the 3. A little bit I didn't say much about it, but now I want to say what was known, what is known in high dimension, and I think Marek Lasak proved that the number in dimension d is smaller or equal than 2 to the d minus 1 plus 1. So maybe even smaller or equal. So this was a very nice concrete bound, which gave fairly nice bound for small values of d. And then Obed Shlam in the 80s proved that every set of diameter 1 in RD can be covered by square root 3 divided by square root 2 plus little of 1 to the power d of sets. So this was the result of Oded Shram. What was Oded Shram's idea? First of all, he said, of course, it's quite easy to see that the Borsuk problem can be reduced to the case of convex sets. And it's also easy to see that it can be reduced even to sets of convex sets of constant widths. So I hope you're all familiar with that there are sets of constant widths like the Rayleigh triangle. It's not easy to spell Rayleigh, but you can talk about this triangle even without spelling the name of the inventor. The Rayleigh triangle is a famous example of sets of constant width, which of course are not are very different than the circle. And every convex set of diameter 1 is included in a set of convex width of diameter. So I should say that not all the people know that there are sets of constant width that are not poles.
But what do you do in higher dimensions? The Rayleigh triangle extends to higher dimensions?
Yeah, this is an excellent problem. So actually, in higher dimension, the sets of constant width is a mysterious set, but it's known that in any dimension, that every convex set of diameter, of given diameter, can be extended to a set of constant width, where the width is the diameter.
Okay.
So this is true in any dimension, and I will talk a little bit about the extension of the Rayleigh triangle. I should say I have I got a birthday gift 10 years ago. Here is the 3-dimensional analog of Rayleigh triangle. I don't know how I can show it to you, but see, this is like a Rayleigh triangle, but it doesn't have the symmetry. And I have 3 of them, which is very convenient. You can You can put a book on them and see that you can roll it and it will be on the same height. So this is very nice instrument.
It's unfortunate that the talk is not in person, but
yeah, but here I can show it to you. Okay. Okay, so I should say that the theory of sets of constant width is very interesting in high dimension. There are you have also something. There is much interest in centrally symmetric convex sets because there are norms of Banach spaces, and the only centrally symmetric convex set of constant width is the ball. So in some sense, this is a theory which goes in orthogonal direction to Banach, to geometry of Banach space, and they're very nice problems. I'll mention one problem in a minute. In any case, Schramm proved that f of d is smaller or equal than square root of 3 divided by square root of 2 plus little of 1 to the power of d. The way he proved it is first he used the norm reduction to set of convex of constant width, and then he showed that every set of constant widths can be covered by this number of smaller homotets of the same set. So this was a stronger result about set of convex widths. So I remember that Schramm gave a talk in our seminar, and Yoram Lindenstrauss was interested in the result. And of course, at that time, the conjecture was b+1, so it didn't look so overwhelming, this number, square root 3 divided square root 2 to the power d. And a few years later, Lindenstrauss found another proof of the very same bound, using a different strategy. And their strategy was not to use sets of constant width, but to use balls. So they proved that every set of diameter 1 can be covered by this number of balls of diameter 1. So this was a different strategy. And so far, this bound for almost 40 years, it was not improved. So it looks that it should be improved, the upper bound, but it was not. Now, as far as the lower bound, Jeff Kahn and I, we found a proof that the f of d is exponential in the square root of the dimension. So we proved that f of d is bigger than 1.2 to the power square root d. So although this does not refute the conjecture for small values of d, because of the asymptotic behavior, eventually it overwhelmed the linear function d+1, and we show that when d is 1,325, then the Borsuk conjecture is no longer true. And since then, there were several improvements of different, with all sorts of very nice ideas. One improvement used the Leach lattice. There were some improvements which were based on just improving our techniques. And the world record is by Bondarenko, who found an example in dimension 65 of a set of diameter 1. And what is special about Bondarenko's example is that cannot be covered by 66 sets of smaller diameter. It is a set which is called a two-distance set. The pairs of points in this set have only two possible distances. And this is a very nice set. And now going back to sets of convex constant width, I should mention a very nice conjecture or question by Oded Schramm. So the question is the following, and this shows how little we know about sets of constant width. Are there sets K in RD of constant width 1 so that the volume of the set K, is smaller than 1 minus epsilon to the power D times the volume of the ball of constant width 1. So is it true, are there in existence sets of constant width 1 which have volume which is exponentially smaller than the volume of the ball? And this is not known. And if this is true, or some variant of it for spherical sets, then this will allow to improve the constant square root 3 divided by square root 2 to square root 4 divided by square root 3. So this will be an improvement. It's an interesting problem on its own. Now we have Oded Schramm, he even proposed a very concrete example of an inductive construction of sets of constants with 1 in dimension D. So you have a set of constant with 1 in dimension D. You can do some tricks, a very simple trick to build a set of constant with 1 in dimension D plus 1. You do something. You put this set in RD inside RD plus 1. You do something above for the new coordinate when it's positive. You do something else when it's negative. And if you start from the line segment, the first step you get is the Rayleigh triangle. To start with the Rayleigh triangle, then you do something. You get something very similar to this guy. So you get something. I'm not sure that this is an example, but below the Rayleigh, here you don't have the Rayleigh, because here this is it looks like a circle here. But in any case, I think this is Oded construction if you start with a pole and apply this construction. And even for this example, we don't know what is the volume. We cannot even. So this is a very nice question. So now what I want to tell you is I have two things on my agenda. One thing is to tell you about various problems related to the Borsuk conjecture, mainly in the plane. And the other thing I want to tell you is how to save the Borsuk conjecture. As I said, there are some obvious questions, so let me mention them. Perhaps the most clear-cut question about Borsuk question is if this function f of d, is it exponential in d or lower? Our lower bound is 1.2 to the square root d. I think this was slightly improved, but the square root d was not improved. And the upper bound are some constant to the d. So the question, what is the truth? I think it's reasonable to guess that the truth is exponential in d. Maybe there are some construction based on error correcting codes, maybe algebraic error correcting code. And there were all sorts of ideas, but all of them failed. So this is completely open. The other question is what happened in low dimension. So the record now is 65. Is the Borsuk conjecture correct in dimension 4 and 5 and 6? So this is also completely mysterious. But I want to talk about something slightly different, which is, can we still save the conjecture? We did something irresponsible by finding counterexamples to the conjecture, and now we need to save it. And okay, so maybe before I move to the problems in the plane, I can tell you about two ways to save the conjecture. One way, which I really like, so how to save the conjecture. So there is one variant that I don't know if it's false, but maybe if P is a polytope in RD, with M facets, then P can be of diameter 1, then P can be covered by M convex sets of smaller diameter. So this is a vast relaxation of Borsuk conjecture, which might be true. I don't know if it's false or not. Of course, yeah, so every polytope is at least D+1 facet, so this is always weaker than the Borsuk conjecture, but this might be true. So I don't know. But here is another way, and I will, and here is the idea. The idea is that counter examples to Borsuk conjecture are truly pathological. So, you know, the conjecture is true, but the counterexamples are there by some sort of coincidence. We should not remove the conjecture, but we should somehow not allow this counterexample. So this is a general approach to life, how to face reality in general. But let me specify to this example, and I will do it for the finite problem. And the idea is, so I call so let X be a configuration of a point in RD, and consider the graph of point in RD of diameter 1. Consider the graph of distance 1 pairs. And then there is the following conjecture, if, let's call this graph the graph G. If G is stress-free, then G is D+1 colorable. Okay, so this is the conjecture, and I should explain what does it mean stress-free. So a stress, if we have a graph embedded in RD, a stress is assigning of weights to the edges so that every vertex is in equilibrium. So if we look at the sum, of the edges from this vertex with the weights and sum them up, we get 0 for every vertex. So this is called a stress. And in a sense, a stress, okay, so this is only related to an area which is called a rigidity or framework rigidity. And to say that the graph is stress-free is some sort of general position of the configuration of points. And this can be extended also to the infinite problem, but it's a little bit more cumbersome. And then the conjecture is that if the graph of maximal distances is stress-free, if the max distance graph is stress-free, then its chromatic number is less or equal to D. So this is a conjecture which is very generally different in nature than Borsuk problem. For example, if a graph is stress-free, it means that the maximum it always has a vertex of a degree at most 2D. So the chromatic number is always between D+1 and 2D. So it's not exponential as in the original problem, but the conjecture is that you can put it all the way to D+1. And I think this is it's a nice question, at least a noble attempt to save the original conjecture. And I didn't fully justify it, but there are reasons to see that this will say that if you have a set of diameter 1, unless something unusual happens, then it will be stress-free, and then the conjecture is that unless something unusual happens, then the original conjecture. Okay, so now I want to talk about 8 problems on coloring circles, and as you will see, and this also goes to Shafar's comment, they are related in theory to Borsuk problem, but maybe first, are there any questions about Borsuk problem or remarks? I see there is one thing in the chat. Okay, yeah, this. Okay, so I should say that today on the archive, there was a paper with claiming a new proof to the four-color theorem using enumeration. Of course, any such claim should be checked very carefully, but at least I know one of the two authors, so it's interesting. Anyway.
So it's yet another computer proof.
No. So this is the human proof.
You said human.
No, the authors are human, and also the proof is human. Okay. It's you. Yeah, there was actually, this is an interesting story. There was a program by William Tatt, a very elaborate program to prove the four-color theorem using properties of enumeration and properties of the chromatic polynomial. Essentially, the idea was to prove that the number of graphs, planar graphs for planar triangulation that can be colored by 4 colors, to enumerate them and to enumerate all the triangulations and to show that these two numbers are the same, which will prove the 4-color theorem. And they use some of the machinery. Look, this is a very short paper, but essentially they use the machinery of Tatt, some other results, and the idea that if there is a counterexample to the 4-color theorem, this implies something asymptotic about the number of non-4-color planar graphs, and this asymptotic statement already violates something that they can. But this is a very short proof. Look, the common sense attitude is to be very, very, very skeptical, but then even, and perhaps to read and try to understand what's going on. In any case, I heard it from Nati, interesting news. Okay, so here are 8 problems on coloring circles, and you will identify some. You will identify also our. Want to use a mouse which does not belong to. So consider a final family of unit circle. What is a minimal number of colors needed to color the circle so the tangent circles are colored with different colors? So this is the famous unit, the chromatic number of the unit distance graph. This is the problem posed by Abigail and Nelson. And due to recent, few years ago, work by also the Gray, the answer is 5, 6, and 7. Let me mention that Moshe Rosenfeld asked about coloring when two vertices in the plane are adjacent, if the distance is an odd integer. And the Rosenfeld conjecture that the chromatic number is infinite. And this was recently proved by Davis. Maybe in a matter of few weeks ago, there was a paper on the archive, and it looks very solid. And so this is a Rosenfeld conjecture. You can ask the same question, but not for arbitrary circles, but for non-overlapping circles. And such graphs are called penny graphs, and then the answer is 4. And the reason is the 4-color theorem. If you have a collection of circles and that are non-overlapping, then the graph of tangencies is a planar graph. So you can use the 4-color theorem. Okay, and now you can ask the same question, but this time not with, yes?
The same question if for unit circle it's 3, it's not 4.
No, for unit circle.
If they are non-overlapping in unit, then it is 3.
No, it's 4.
So you're saying unit and non-unit is the same?
Yes, if they are non-overlapping, yes.
Maybe I'm missing.
Yeah, if they are not unit circles, then you can realize every planar graph. If they are unit circles, this poses some restriction, but still there are examples where you need the 4 colors. And you can now ask where the circles are pairwise intersecting, and then the answer is 3. And this is the finite version of Borsuk problem. This is precisely the finite version of Borsuk problem, because you have here a collection of points. You look at the circles, so if they are non-overlapping, it means that the distance, that the graph represents the maximum distance. And then the Borsuk problem says that you can divide them into 3 parts. And if they are non-overlapping but not unit circle, then again you can apply Kelbe's theorem and the 4-color theorem, and the answer is 4. Now, if you consider the case that they are neither unit and you don't pose any condition, then as far as I know, so you don't pose that they are unit distance, then there are examples where it's bigger than log n and smaller than log square n, so it's no longer finite. And then there is the famous Ringel circle conjecture that you impose another condition that every point is included in at most 2 circles, but then so Ringel conjecture that a finite number of colors suffices, but this was refuted in a recent work by Shachar Wizir and James Davis, Chaya Keller, Linda Keist, and Baruch Rothschild. And there are interesting questions when you replace a circle with pseudo-circle. And it's challenging both to pose this question in the correct way, and this leads to very fascinating questions. So I will not mention it. I should say, perhaps one of the answers, let me mention just, okay, here it is. There is so this question gives rise to various unit distance graphs. And one of the variant is that you have unit distance graphs when one is the maximum distance. And this is precisely the graph whose chromatic number is the object of the Borsuk problem. And in the plane, there is an old theorem of Hoff and Ranivitz, which says that if we have planar geometric graph, if you have more edges than vertices, then you have 2 disjoint edges. And this is a very nice theorem. And as Shachar mentioned, if you consider instead of line segment curved pseudo intervals, then this is the famous Thrakel problem four-way. It is not known that this continue to hold if you have a collection of, so suppose you have a collection, you have endpoints, you have collection of line segments that every two line segments cross one another. Then the number of line segments is as most the number of vertices. This is the famous notorious open problem of Conway, which is still open, and it's a very exciting game. So, had I have more time, I could show you a nice proof of, yes.
I think that for straight line segments, this is the famous solution of Micha-Perles. For non-straight line segments, it's a conjecture, isn't it?
No, yes. For a straight line, this is the result of Hopf and Panifitz.
No, I'm talking about Thrakel.
What is Thrakel? Yeah, no, okay. But they also prove that if you have the way they prove this result about the unit distances is that they showed that if you have more edges than if you have more edges than vertices, then you have two disjoint edges.
No.
So this is the result. That you have two disjoint edges, and this is not known for pseudo edges. And Micha-Perles, 50 years later, found a proof, very nice proof using lice. But the original proof, there are many proofs, and it's fairly a nice result. So maybe I will not give Perles proof, and